So one of the things we studied last time was this concept of correlation length and pair correlation functions in the concept of spins and things like that. Right? We talked about broken symmetry, and we drew a picture where we talked about the Helmholtz free energy of magnetization, right? For a 2D Ising model. For 1D, we did not really, it's for a 1D, we know it's just going to be boring. Nothing really happens. For a 2D Ising model, we said that it's going to look something like this. There will be a barrier A star. And as we decrease the temperature, this barrier will become smaller, right? So this is T is equal to T1. The red is T is equal to T2, where T2 is, sorry, I did not mean smaller. T2 is larger than T1. As we increase the barrier, it makes it easy for things to go back and forth. Right at the critical temperature, it looks something like this. And that is to be distinguished from what happens beyond the critical temperature. Beyond the critical temperature, there is only, so notice that under the critical temperature, there are two states. There's a barrier for moving between them, right? So you can get trapped for a long amount of time. As you get closer and closer to critical temperature, but staying slightly below it, it's not like the basins have disappeared. The barrier has disappeared. The basins are still there, right? But once you go above the critical temperature, once you are very much higher above the critical temperature, it will look something like this, right? You will never have ordered states. You will always like to be somewhere disordered, right? So I want to emphasize this point. So notice the difference between what happened from red to blue to green. Red is when you have two things. And in terms of who works in atmospheric sciences here? You are in atmospheric sciences. What do you work on? Ozone layer. But even so, you know, like in the atmosphere or even in the ground, when you have ice forming, like when up above, there is lots of interest in studying ice nucleation, right? Because ice can form in the higher levels of the atmosphere, and that can lead to all sorts of things happening. So nucleation is something we often talk about in chemistry. So atmosphere or more generally. So the red and black correspond to nucleation and growth type mechanism. You can form in the middle of, like when I played that movie, in the middle of everything blue, a little yellow thing was forming. But unless it has to grow over a barrier to go to the other side, right? So it will be thermodynamically trapped because there is a barrier. Once you get to the blue one, there is no barrier. It's not nucleation growth. It's barrierless. It just goes back and forth. So what happens at the blue one, and there is a formula that I wrote down, which was fluctuations were equal to I is equal to 1 or 2 to n. We don't, n is very large, so we don't really care about what it is. Let's just call it 1. I or j is equal to 1 to n C1j. So this is telling us that the fluctuations of the magnetization are correlated to, are the same as the correlation between spins, right? And under the critical temperature, you cannot really fluctuate wild amounts. You are trapped in one of the basins. You will have other domains and things to grow. As you get to the critical temperature, fluctuations diverge as T tend to Tc is approached. Why do they diverge? Because now you have a barrier-less system. Again, if you focus on the blue thing, you can form domains of as short or as big length as you want. There is nothing stopping you from doing that. So in fact, if you think about the correlation length of the system, which is, how do I get the correlation length? I think Noah, you asked this on Slack. How do I get the correlation length from the correlation function? Basically, once I plot the correlation function as a function of distance, it will go to 0, right? Are you really correlated with something that is going on outside this classroom? Probably not. In this classroom, we are correlated, right? If I say something, here is problem number 4 on the final, suddenly all of you are looking at me as you're correlated, right? Something is causing you to pay attention to that. People outside are not doing that, right? So if I look at how the correlation function is dying as a function of distance, the distance at which the correlation function becomes 0 or some small value, that is the correlation length. So what I'm plotting here is the correlation length as a function of temperature. At low temperature, there is some correlation length, and it diverges as you get close to the critical temperature, and then above the critical temperature, it goes to 0. So this is the plot that I posted on Slack. So at low temperatures, it does not go to 0, it becomes some finite value. And the fact that you have a finite, why is not the correlation length diverging as we go to low temperature? Because you would think that at very, very low temperatures, the system should just become one block of the same spin, right? So the correlation length should become infinite, but that's not what would happen. You will have domains, right? And the correlation length will be given by the size of the biggest domain. It's like if you made a crystal, and a single crystal is very, very hard to make, right? You will have some grain boundaries inside it, and that will sort of set the limit for things like that. But this as you approach the critical temperature is going to diverge, and it diverges as something like a power law. And there are these critical exponents, and we'll talk about that in just a moment. So, and there are, you can find, in fact, water has a critical point at which you can see how fluctuations become like at any time, at any length, you can see fluctuations. You can go, and there are all sorts of strange behaviors that happen at critical temperature. One of them is called critical opalescence, because the correlation length has become so high that it reacts with light in a very different way. So studying the critical temperature is of huge interest to a lot of people. So that's all I wanted to say about this. And now I want to move to renormalization group theory. So why do I want to do renormalization group theory? So I want to calculate the critical temperature of the Ising model. I want to study phase transitions in the Ising model. Even though the Ising model is a very simple model, it's a good system to simulate many, many things. Okay. So, and we first looked at the Ising model using the Pearl's droplet argument, which was qualitative, but we got good answers from it. Then we moved to mean field theory, which was completely wrong in 1D, but as dimensions became higher, it tends to become higher and better and better. And it's a nice way to tackle a problem. In fact, many of you will be reading papers, even though you're going to do experiments, you will see papers where people do experiments on some complicated polymer or some quantum dot or whatever. And in order to explain their experiments, they have to come up with a theory. And often the simplest theory they can come up with is a mean field theory. In fact, people like Ami who do quantum chemistry, things like Hartree-Fock theory and all, these are effectively a mean field theory that was first made up to think about how do electrons behave. So you will be seeing these mean field type pictures where you assume, yes, you account for the many things being there, but on an average, their behavior is the same. And everything looks at everything else in an average sense. That was the idea. But mean field theory it's okay. It does not really get the job done. So that's what led to people thinking about renormalization group theory. And renormalization group theory, the original ideas, I think, existed in quantum mechanics, in quantum field theory since 50s or 60s. But it's really Ken Wilson who did a lot of work on it, and he got the Nobel Prize around 1970s. And as I said, this is an IPST connection because Ken Wilson's work was built up on Kadanoff's work and Michael Fisher work. Kadanoff was a professor at University of Chicago. There are some very good videos of him on YouTube where at age 90, he was riding his bicycle around Chicago, being very happy about science. He's a cool guy. It's inspiring if you watch his videos. And Michael Fisher, of course, was in IPST for many decades. His son, Daniel Fisher and Matthew Fisher, both are scientists. I think it's one of the only families that I know of where the father and two sons, all three are in the National Academy of Sciences. It's kind of rare. And his son once came to give a seminar here, and Michael introduced him. It was a very short introduction. It was like, "This is my son. Welcome." And he stopped. Maybe because, yeah, anyway, so that was Michael.
What do you need to know?
Michael Fisher was also Michael Fisher was very much against Monte Carlo simulations. There is a very famous Michael Fisher quote: "The only good Monte Carlo is a dead Monte Carlo." But then people like Landau, whose paper you read, Wang Landau, convinced him like, no, it can actually be useful. But Fisher was very much pen and paper. He did not even like computer simulations. So, okay. So, and there are, I will post some papers on you can read up Ken Wilson's Nobel Prize lecture on this topic, which is quite useful. And over the years, there have been many other Nobel Prizes where people have done renormalization group type ideas in some other context. So it has become a staple in physics. And the idea is quite simple. And I will introduce the idea in terms of a 1D Ising model that I will solve more carefully. Then I will show you how it can be done in 2D, and you will get the same basic idea. So let's say we have a 1D Ising model where I have some spins arranged along a 1D lattice that looks like this. Okay, so let's call this S1, S2, S3, S4, S5, dot, 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 something like this. So the idea is, okay, I can look at everything one spin at a time. But what if I decide to ignore every even spin or every odd spin, whichever you pick? What if I try to look at the system every other spin at a time? So what I have done in this procedure, I have reduced the number of spins by 2. What is the physics of that system going to look like relative to the physics of the original system? The physics might be very different, but maybe it will be very similar. So what renormalization group theory does is to take the physics, and this procedure of removing spins is known as decimation. Decimation means, like after next week's exam, you might be like, I feel decimated. It's like, I feel destroyed, So you're destroying. I hope you don't feel that way. It's destroying every other spin. What do I mean by destroying? I don't mean I just take it off. No, we are going to talk about an Ising model where the Hamiltonian is minus J summation SIFJ nearest neighbor. What decimation means is to average out the behavior of every other spin. Okay. So renormalization group theory says if you decimate or remove, which really means average out over these other degrees of freedom, can we connect a relation of this decimated system with the original system? And it works quite well. One of the successes of renormalization group theory was, just like I plotted the correlation length over here, how it diverges at the critical temperature. It's not just the correlation length. Close to critical temperature, many other thermodynamic observables like the heat capacity diverge. The heat capacity, we know, now you are all experts on heat capacity. At low temperature, it should in general go to 0. But right at the critical temperature, the heat capacity diverges. And on the other side of the critical temperature, it also diverges. And both of these show some behavior that depend as power law. And often the slopes on different sides, they don't have to be the same. They could be different slopes. These exponents that you are seeing here, they are called critical exponents because they are associated with critical behavior. So renormalization group theory allows you to calculate these critical behaviors, critical exponents to very high accuracy. And anytime you see power law in the physical system, generally speaking, there is some sort of self-similar behavior going on. There is some sort of fractal involved. So in economics, in finance, power laws show up all the time. If you plot the returns of the stock market over a function of time, it won't look like a Gaussian. It will look like probably like a power law. And often it means that these renormalization group type ideas can actually be applied there. Behavior of two people trading with each other is not very different from behavior of two countries trading with each other. There is some similarity and things like that. And so let's work through this. How?
I have a question.
Yeah.
So I get that, like, theoretically, in this case, the heat capacity diverges, but like in practice, if we have like a real material, it won't have like an infinite value for that quantity, right? Because like it's not physically meaningful for it to be.
Well, it will keep increasing, and the closer you get to critical temperature, the harder it will become to heat it. So you will reach practical limits at some point, but it will keep increasing. The as you get closer to critical temperature, you'll find you have to pump more and more heat.
Can those like practical limits tell us anything about the physics?
Maybe. I mean, sooner or later you will run into non-equilibrium phenomenon before you know it and things like that. So this type of machinery will fail. So there will be some other limits that will happen. So let's start with the 1D Ising model. In absence of this, I wrote it H, but just to simplify things, let's call it E nu, the energy of a microstate. So we will start with E nu equal to this much. For this equation, let's call this equation number 1, and we will study this. So, okay. So we have a 1D Ising model with nearest neighbor interaction. E nu is equal to minus J summation Si Sj, where I and J are running over nearest neighbors. So let's write it down explicitly. Let's break it down. And I'm not going to worry about what's happening at the boundaries. Let's say there are lots and lots of spins. I'm not going to worry about what's happening at boundary. So I will write it as S1, S2 plus S2, S3 plus S3, S4. You might say, what about the left side of S1? Well, it could be S0, it could be S minus 1. I don't care. I'm just writing it down this way. So this is the, huh?
S1 is n, it's a ring or something.
Yeah, it's just a number. It's a counting. There is always an S0 and S minus 1 and things like that. Okay, so it's not flat earth. So what I'm going to do now is to introduce a new variable because J is in units of KT. So I will call a new variable K, which counts how much is J in multiples of KT. Okay, so K is going to be J over KBT or J multiplied by beta. In other words, beta is now J by K. Inverse temperature is given by J by K. Okay, I'm just going to switch this thing. And the reason why I will do this is because anytime I write e to the power minus beta E nu, I will have beta J automatically equal as K. So I will have some simplicity. And there is more reasons why to do this. So my partition function, the canonical partition function for the full system, Q of beta n, is the same as writing Q of Kn, right? You can remove beta and think about K. Because now instead of K is capturing the value of beta. It's beta multiplied by J. So I'm going to write down Q of K comma n. And that is going to be summation mu e to the power minus beta E nu. So if you put the value of E nu in this equation, if you put this thing over here, if you put value of E nu in this equation,
Dr. Kumar,
yeah.
You wrote the definition for beta rho to be K over J, right?
I didn't want to say it, but yeah.
Or is human. Or ChatGPT also makes mistakes. I don't know what is human anymore. So beta is equal to J by K by J. Yeah, good. So now Q of K comma n is this minus beta E nu. When you multiply E nu with minus beta, you get beta J, and beta J is K, right? So this becomes summation over nu. What is nu? Nu means looking at S1, S2, S3, plus minus 1 value for all of them. EXP of K dot 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 S1, S2 plus S2, S3 plus dot dot dot, something like this. Okay, so now I'm going to average out. For those of you who like probability theory, technically what I'm doing is I'm marginalizing out. I'm averaging over the behavior of every even spin. S2, S4, S6, I'm going to do that. So how do I do that? In order to do that, I will take my equation 2 and write it in the following form. Q of K comma n is equal to summation S1, S2, S3 e to the power exp of K S1, S2 plus S2, S3. Let's group these two in one exponential multiplied by exp of S3, S4 plus S4, S5 dot multiplied by exp of S5, S6 plus S6, S7. I've done nothing profound, right? Just it's an exponential. Exponential is a product of individual things. So I've just split it in groups of 2. But notice now that S2 shows only in the first one, right? S4 shows only in the second one. S6 shows only in the third one, and things like that. And how many values can S2 take? +1 or -1. So I can take this first one and actually write down both values of S2 that are possible. Same for the second one. So in that case, my summation will no longer run on S1, S2, S3. It will run only on S1, S3, S5, because I've explicitly provided the value of S2 and S4. Okay, so let me write it down, then it will become clearer. So now I have S1, S3, S5, and in this first expression for S2, it will become exp of K S1, S2 plus S1, S3, S1, S2 plus S2, S3 when S2 is equal to +1. How much is that? That is S1 plus S3. This comes from S2 equal to +1. And then I will have, and this is a summation now, so it's going to be plus exp of K, and now I have to take the value of S2 is equal to -1 minus K S1 plus S3, right? This, all of this is when S2 is equal to -1. And together, this whole thing is just this one EXP, okay? If S2 took 3 values, I would have 3 exponentials, sums of 3 exponentials, right? So I can write it down explicitly. Then I will have other terms corresponding to this one. Same thing. Now S4 can take +1 and -1, and you write it down explicitly, right? So let me write down this expression again on the next page. So if you have not copied, don't worry, I'm writing the whole thing again. So I have just shown that Q of K comma N can be written as a summation that runs over S1, S3, S5. And it has terms now which are not just exponentials. In the original Ising model, it was a product of exponentials. Now it is a product of sum of exponentials, two exponentials at a time. So this is going to be EXP of K S1 plus S3 plus EXP of minus K S1 plus S3 multiplied by EXP of K. Now it will be, so this was when we got rid of S2, right? So now we are getting rid of S4, so it will have S3 and S5. So this will be K S3 plus S5 plus EXP minus K S3 plus S5 dot dot dot. So this is QKN. This is equation 3. And without any doubts, this looks awful, right? This is not like an Ising model. We took it, we removed spins, but now we got something which is extremely, extremely complicated, right? This looks awful. But
let's do it again.
No. That would be like the show Severance, if you have seen it. You hate it. Has anyone here seen Severance? You hate it, and the next day you're like, what? I have to do it again. You keep doing it, you're stuck. So this, any of this thing, let's write it general, not just S1, S3, let's consider S and S prime. For any two S and S values, if for any S comma S prime, where S comma S prime could be S1, S3, it could be S3, S5, it could be S5, S7. If this thing that I have above here, EXP K of S plus S prime plus EXP minus K of S plus S prime, if this thing could be written in the following form, and it will look very strange what I'm going to write next, but you will see why it makes sense. If it could be written as something which is f of k, some function of k, which we don't know what it is, multiplied by e to the power k prime s s prime. Let's call this equation 4. If this would be true for all s comma s prime equal to plus minus 1, if we could find, if we could show that there exists, so I have introduced two new variables here, right? I have introduced f of k, a function. What I know k is my beta multiplied by j. I have introduced some function of k, and it could be any complicated function. I don't know what it is. But if there exists such a function, and if there exists a new number k prime, which follows these two things, which follows this equation, then my life might become very simple. Why might my life become very simple, you say? Because of the following reason. Now, if I look at q of k comma n, and I write it as S1 summation over S1, S3, S5 dot dot dot, this first thing that I have over here, that will be f of k multiplied by e of k prime S1, S3, right? The second thing that I have will be f of k multiplied by e to the power k prime S3, S5 dot dot dot, right? because I have just said that what I have done here is to say, let's assume for now that the sum of these two exponentials can be written as just one exponential multiplied by something else. And we'll get to the math of that in a moment, whether it's possible or not. And that is really the whole RG theory in a sense. When can this equation be possible and what we can do with it? If we can write it down in this way, then this complicated looking expression in equation 3 simplifies, and original system had n spins, right? And now we removed half of them. So this will mean that we will be left with f of k to the power n by 2, which can now go outside the summation because k is just a number and f is just a function. I don't know what that function is, but it is just a function. It does not depend on spins. It can be dropped outside the exponential. And I will have here s1, s3, s5. And inside, I will have e to the power k prime multiplied by s1, s3 plus s3, s5 plus s5, s7. Now that is just the Ising model, right? It is an Ising model where the prefactor, where the j term has been changed, the coupling is different, and spin number 1 is talking to spin number 3, spin number 3 is talking to spin number 5, spin number 5 is talking to spin number 7. So you have k prime, and you have an so the coupling is k prime. The k prime has changed, and up front, instead of just having a number 1, you have something else, right? So this is just the Ising model with a very different set of interaction parameters. All of this would be happen. So let's call this equation 5. And equation 5 can happen only if equation 4 is possible, right? So, and before we get into whether equation 4 is possible or not, let's see why it is worth thinking about. What is the advantage of equation 5? So equation 5 is very similar to equation 3. What was equation 3? Equation 5 is equation 5 is very similar to equation 3. No, equation 5 is not very similar. It's same as equation 3, except it looks much simpler. You have some interaction that looks just like the Ising model. And notice, let me write it down again. So what I just showed, equation 5 is that q of k comma n is equal to f of k to the power n by 2 multiplied by s1 summation over s1, s3, s5 e to the power k prime s1, s3 plus s3, s5 plus dot dot dot. Can I think of this summation in terms of a partition function? If this was the partition function of a system with n spins, how many spins does this partition function have? N over 2, because I have decimated half of them. So this can be written as q of k comma n is equal to f of k whole thing to the power n by 2 multiplied by the partition function of a system with coupling k prime and half the number of spins, right? That is an important equation. Again, this is going to be true only if equation 4 was true, but we'll get to that in a moment. Let's call it equation 5a. This has a name. This is known as a Kardanov transform. So you have transformed the partition function of a system with n spins and a certain amount of coupling k to the partition function of a system with half the number of spins and some other coupling k prime, right? And remember, coupling k is not just j, it includes value of temperature. So this could be really powerful because you could be looking, if you want to keep j same, this allows you a way to change the temperature. You could study the behavior of a system at one temperature by looking at half the number of spins at another temperature. So it opens up a very powerful relation. In math, such relations where you have functions on the one side and the same function with some other variable on the other side have a name. What do we call them? It's a recursion relation, right? So it's like f of x plus y is equal to f of x plus f of y, something like that, right? So this is example of a recursion relation.
I have a question.
Yeah.
What if we were working in an ensemble where we have chemical potential instead of a fixed number of particles?
You could generalize this for all sorts of things. The math would be slightly different, but the same type of idea can work there also. It's really powerful. People use it for gazillion things.
Okay.
It's super powerful. So this might be useful, and I will show you why this would be useful. But for this to happen, we rely on equation 4 to be true. Only if we could write down something in the form of equation 4. So let's try to look at equation 4 more carefully and see whether it is even possible. So equation 4 was exp of k s plus s prime plus exp of minus k s plus s prime is equal to f of k e to the power k prime s multiplied by s prime for all s comma s prime equal to plus minus 1. So this is one equation which has to be true for 4 possible combinations of s and s prime value. So how many equations in total? 4. Who thinks 4? Who thinks 2? It will turn out to be 2. We can write down all values of s and s prime, and you will see that 2 of them give the same equation. How many unknowns do we have here? We have 2 unknowns, f of k and k prime, right? If it was 4 equations and 2 unknown, then it won't work. It turns out there is actually only 2 equations. So we can write it down explicitly. For s is equal to s prime equal to plus 1, what do we get? This one becomes s plus s prime becomes 2, right? So we get e to the power 2k plus e to the power minus 2k is equal to f of k multiplied by, now s multiplied by s prime is equal to plus 1. So f of k multiplied by e to the power k prime, right? Then we go to s is equal to s prime equal to minus 1. What do we get in that case? S plus s prime is going to be 0. So e to the power 0, which is 1. Again, e to the power 0, which is 1. We get 2 is equal to f of k multiplied by e to the power minus k prime, right? We get 2 equations. Now, no, I wrote it wrong. This will, should not rush, sorry. S is equal to s prime is equal to minus 1. That won't give me e to the power 0, right? S plus s prime is now minus 2. So I will get e to the power, sorry about that, minus 2k in this one. And what will be the right side? E to the power plus 2k. And then this will be f of k. And what will be this? E to the power k prime. S multiplied by s prime is still the same. It is plus 1. E to the power k prime. Did we get a new equation? We got the same equation, right? So one of the cases already gave us a repeated equation. This is the same equation. Now we go to s is equal to plus 1. S prime is equal to minus 1. In that case, s plus s prime is now 0. And we get 1 plus 1. 2 is equal to e to the power. 2 is equal to f of k multiplied by e to the power minus k prime. And when you get to s is equal to minus 1, s prime is equal to plus 1. Once again, 2 is equal to f of k e to the power minus k prime, right? So we get 2 equations. The first equation is e to the power 2k plus e to the power minus 2k is equal to f of k multiplied by e to the power k prime. And the second equation is 2 is equal to f of k multiplied by e to the power minus k prime. Let's call this as equation 6. Let's call this as equation 7. So we have 2 equations in 2 variables. We can solve for k prime. We can solve for f. I will pick up speed just a bit because I also want to recap. You can read the algebra in the Kardanov paper, but basically what I get is K prime is equal to half ln of hyperbolic cos of 2K, and f of k is equal to 2 square root of hyperbolic cos of 2K. It's really literally 3 lines of algebra to go from last page to this one. All I have done is to take 2 equations and solve for two unknowns. So in my notes, these are numbered equation 7a, so that's what we're going to call them. So what does this first equation mean? The first equation means is K was the coupling parameter for a system with n spins, and K prime is the coupling parameter for a system with n/2 spins, and they're connected. You can write it down this way for Ising model in 1D with nearest neighbor interaction. And in fact, f of k, this new function that we introduced, is also explicitly dependent on k. It's not a trivial dependent, it's a square root of a hyperbolic cos, but it is just a function. So equation 4, which we wrote down, which was our ansatz, if it is possible to write down in that way, is actually solvable. It works. We can get this connection. So, okay, there is a bit more math before we see the power of this. So I have been thinking about the partition function, right? Q. I have been thinking about Q of n comma k. What I'm really interested in is ln of Q, right? ln of Q gives me the free energy. So what I'm going to do is to take ln of Q and divide it by n and call it as g of k. This is some intensive free energy. Okay, and I should have written down a minus sign, but it doesn't matter. It's the log of partition function, which is an extensive quantity, free energy, divided by n, which becomes intensive free energy. Why do we want to look at intensive free energy? Because we're changing the number of spins, right, in this case. So what Noah asked about a system where the total number of chemical potential is constant, all of this will be harder, but I think people have done it. Here we have fixed number of spins, we removed half of them, and now we are looking at something. So if you look at equation 5a, which was this recursion relation between Q of Kn and Q of K prime comma n/2, we can take the log of both sides. Okay, so natural log of, or any log, I don't know why I wrote natural log, on both sides will give us ln Q of K comma n is equal to, so if I take log of this, that becomes ln Q. Log of this will become n/2 log of f of k, right? It's the property of the log, and then a second log. So this will become ln Q of n is equal to n/2 natural log of f of k plus natural log of q, which is now is the same function, because why is q the same? Because the Hamiltonian was the same. The energy of a microstate was again sum of product, sum over e to the power s1 k prime s1 s3 plus s3 s5. So it's the same. It's going to be the same partition function. The coupling is different, k prime, and the number of spins is different, n comma 2. So if I take this and divide by n, I want to do one more manipulation. I want to write down this as ln of q of k prime n/2 is equal to ln of q of k comma n minus n/2 ln of f of k. I divide both sides by n/2. What is this in terms of the intensive free energy I just defined above? This is g of k prime, right? G of k was take log of q and divide by the number of particles. In this case, number of particles is n/2. So this is g of k prime. What is this one? This is 2 g of k, right? minus n by 2 cancels, minus ln f of k. And remember, we solved for f of k. We can bring that over here, and that becomes 2 square root of hyperbolic cos of 2k. Now, this is equation 8, and this is a recursion relation between the free energies of two systems with different coupling constants. This one is very important. This is known as the central renormalization group equation. And this is what we are almost there to take this to our advantage. What is this telling us? This is telling you start with one value of k prime. If you can get the value of g of the free energy for this k prime, then you can get the value of g for some other k prime. So let's see this in action. I'll write down this central equation on the next page, and we will see how it works for the 1D Ising model. So I had the central equation as g of k prime is equal to 2g of k minus ln of 2 square root of hyperbolic cos of 2k, something like this. So let's start with k prime, very small, almost 0. Central RG equation. Central RG equation. If I start with k prime is equal to 0, and n spins. At this point, notice I have gotten rid of n in my equation. So what I'm doing might seem a bit strange because we started with decimation, but now I'm going to start with n spins. Okay. So let's say I have a system comprising n spins where the coupling constant is 0. What is going to be the partition function for such an Ising model? No. How many sums? Think carefully. What is partition function? Many more than n. How many more? E to the power minus beta e nu, right? If there is no coupling, what is the value of minus beta e nu? 0. There is no interaction energy. So this is summation S1, S2, plot e to the power 0 or 1. So if you have n spins, how many microstates will you have? 2 to the power n. Does everyone see that? Every spin can take plus minus, and there are n spins, so it's going to be 2 to the power n. It's not going to be n, right? So this is going to be 2 to the power n. In fact, this is the only Ising model for which we can write down the partition function explicitly. There's 2 to the power n number of microstates, and each microstate contributes same weight, 1, because there is no interaction. If there was the tiniest amount of interaction, we cannot just write down 2 to the power n. Then we know the sum will be a bit different because we have to go and calculate e to the power minus beta e nu for all those microstates, right? So this is 2 to the power n. So what RG does is say that, okay, this means that g of 0, if there was no interaction, g of 0 is going to be ln q by n, right? That is how I define my intensive free energy. What is ln q? That is n ln 2 by n equal to ln 2. So RG says this is true for exactly k prime is equal to 0. But if you use this in this equation number, in the central RG equation, equation number 8, this won't work. So it makes an approximation and say, well, I know it is true exactly only for 0, but how about I assume that I take some value which is ever so slightly larger than 0, right? So I turn out the tiniest amount of interaction. And I say, well, it is so small that I'm still going to assume that it is basically a non-interacting system, right? So I can approximate now that g of 0.01 is equal to ln 2. If you don't like that, well, take an even smaller value of the interaction. Start with 0.0000001. At some point, it will become ln 2, right? It's so small. So you start with this value. It will become more accurate as k prime becomes even smaller. So notice that when I solved for k prime and f of k, I had now a relation connecting k prime to k, right? So I can put this down over here and I can use that relation. K prime is equal to half of ln of hyperbolic cos of 2k, or k is equal to half of hyperbolic cos inverse of e to the power 2k prime, and e to the power 2k prime is e to the power 2 multiplied by 0.01. This is something you can do on a calculator, right? You can calculate this number and you will see that this gives you k equal to approximately 0.100334. So I took a very small value of k prime. I used that to calculate the value of k. Okay?
I'm a little confused.
You should be very confused.
Yeah, so like when you're doing the G of 0.
Yeah.
Why do you just say that that's equal to ln q over n? Like what happened? Or wait. So,
That's the definition of G. G is defined as G of k is ln q by n. That is how I defined my free energy.
right, I got that part. But why is the second term not there?
Which second term?
The minus ln to.
Because in my definition of G, there is only one term. G of 0 is ln q by n. G of k is ln q by n. Yeah. Yeah. The equation 8 has a second term because you're talking about connecting two possible G's. So that second term will show up exactly now. So now this is where we are going to use it. Now we will use the second term, and we have 2g of k is equal to g of k prime. What is g of k prime? Well, let me write down first. 2g of k is equal to g of k prime plus ln of 2 square root of hyperbolic cos of 2k. When you read these theories, one thing it definitely shows me is before people had supercomputers or even calculators, they thought really, really hard to come up with things like this, right? And I'm really worried that we are going to stop discovering good theories now because it's so easy to just cheat, right? And think of everything. When I started my PhD, data-driven science used to be a cool term. Now I really don't like it. Somehow data-driven now means we are not going to think. Like data-driven sounds like
theory of everything.
There is no way ChatGPT would come up like this. Like it's so complicated, right? Like what are we trying to do? It's super bizarre if you think about it. In a moment you would see how it's quite nice. You have a question, Natalie? No? Okay, good. Yeah, any comments? No? Okay, good. Yeah.
Unrelated question. Can you go back to pages? One more page. There's a factor of 2 that I'm trying to follow somewhere that I'm not seeing because I thought there would be a 2 on the G of k prime on the left hand side as well as on the right hand side because they both have that n divided 2.
So when I divide this one by n by 2, this is the intensive free energy for a system with n by 2 spins. That's why it becomes G by G of k prime, and you don't get a 2 factor. This one is the intensive energy of a system with n spins with an extra 2. No, it's a subtle point. Okay, so now we have this equation and we can work through it. We have G of k prime is what? G of k prime is ln 2. Let me write down this equation on the next page. So we have 2g of k is equal to g of k prime plus ln 2 square root of hyperbolic cos of 2k. So 2g of k is going to be ln 2 plus ln of 2 square root of cos, hyperbolic cos of 2 multiplied by 0. I calculated the value of my k. The k was 0.100334, so now it will be 0.10334. And you get g of k is equal to 0.698147. Okay, what did we just do here? Let me make a table. So we started with a value of k, and now really I don't want to think about k prime or k and things like that. I can just call everything k. I started with a very small value of k, right? Close to 0.01. For that, I calculated the intensive free energy of that system, G of k. For k is equal to 0.01, it is basically a non-interacting system. The partition function becomes 2 to the power n. So the intensive free energy becomes approximately ln 2, right? What is ln 2? ln 2 is 0.693147. For k equal to 0.01, you can also, so this is my renormalization group. intensive free energy. You can also calculate the exact free energy for that K for the Ising model. You can by running a computer simulation, which is very long, or by just summing it up, or whatever you do. In this case, you can also do theory, and you get number which is 0.693197. Start to correct? No, I think it's, my handwriting is terrible. It's 0.093197. It's actually a bit off, right? I have to check that, but it's the idea being that now that when we go to the next value, when we use this value of K and put it in the central RG equation, we got another value of K, right? That another value of K was 0.100334. Let's call that approximately 1. For that, we got our G of K as 0.698147. For this, the exact value is 0.698172. You can keep doing this. If you plug this equation back in and you get the next value of K, you will get 0.327 and whatever numbers you get over here. And you can keep doing this. At some point, you will get to something 2.702146. Before I get there, I want to give intuition on what this really means. So this is increasing value of K, right? The K is increasing as we go down. And in the very beginning, I defined K as, and this is important that Didi corrected me there, that K is equal to beta multiplied by J, right? K is equal to beta multiplied by J. So if the J is constant, then increasing K means increasing beta. What does increasing beta mean in terms of temperature? Decreasing temperature, right? So this is increasing K or decreasing temperature. So for this value of K, the RG value is 2.70663, and the exact value is 2.706634. It becomes more and more accurate as you keep doing this operation. And you could have started with an even smaller K. That does not matter. You would have more steps to get to some temperature. What would happen if you keep doing this again and again and again? You'll get bored at some point. But physically, in a 1D Ising model, what are the things that might happen? What are the possibilities? What do you guys think? K increased, right, as we kept going. So what is the first possibility? K keeps increasing, and we get to some infinite value of K. That's the trivial possibility, right?
Limiting value.
Or we get to some value and the equation says whatever you do, it becomes a fixed point. It does not change anymore, right? And we have fixed point equations. It is like, I'm thinking of that T-shirt, you know, like it's a meme shirt where this guy is walking next to a girl and the girl is saying, I'm going to change you. And he goes like, I'm e to the power x. You can differentiate me as many times. I'm not going to change, right? You know what I mean? It's a fixed equation. Nothing is going to change. Turns out, it's a bad example, but I think it really drives home what I mean to say. In a 1D Ising model, you can start from any K and you can get to any other K. There is no discontinuity. Each K is accessible from any other K. K is equal to very small corresponds to very high temperature. So solving the Ising model, and when we wrote 2 to the power n, that's really, we said, oh, the interaction is 0. But another way the interaction might become 0 if the temperature is very, very high, right? The interaction is very low. So at very high temperature, of course, it's going to be an independent system, right? That's what we saw in StatMech. Everything becomes ideal gas at very high temperature. So we started at a very high temperature, and we were able to get to any value of temperature, right? So we could draw this in terms of a diagram, and in RG theory, people call this a flow diagram. So we started with K is equal to 0 or very high temperature, and that got us to 0.1, that got us to 0.327, and if you keep doing this operation, you can get to any value of K, very low temperature. what does this flow diagram in 1D Ising model? What does this tell us about the 1D Ising model? Is the same partition function that applies irrespective of whatever temperature you take. You are not going to see any different phase. It's the same business that goes on. There is no phase transition. The flow diagram does not have a fixed point. If you go to 2D Ising model, and this is why I posted the Kadanoff picture, there you do decimation in a different manner. There you have spins like this, right? It's a 2D square lattice. There your decimation will be doing something like this. You average out over things like this. Of course, the algebra is going to be a bit harder, but if you understood what I have done today, you can read Kadanoff's paper and you will understand what he's doing there. For 2D Ising model, the flow looks like as following. You start from k is equal to 0, and you can keep going in this direction until you will get to a k is equal to kc, and then it will get stuck. It won't give you any higher values of kc. You can also start from a kc very high. You can also start from a k very, very high is equal to infinite. And then you will see that the recursion relations keeps bringing you to a smaller value and gets stuck at k is equal to kc. So there is an interruption in flow, which means there is something where a phase transition is happening, right? And we have just touched like the tip of the iceberg of renormalization group theory. It just goes more and more from here. There is profound work people are still doing in all of this. But I think it's quite elegant. This simple type of idea gives you something which is quite geometric in the end. We worked through just algebra. It's kind of nice that we got through this. And people think about renormalization group theory in many, many different ways. There was a classic paper in machine learning that came out from David Schwab and Pankaj Mehta. David Schwab was here last year to give the physics department colloquium. We even tried to hire him, it did not work out. Where people showed that if you have a deep neural network and you have neurons and you are condensing the number of neurons in a layer, let's say you have some sort of an autoencoder. And they showed that as you're doing something like this, at every layer of the neural network, perhaps it is doing something like a renormalization group operation. And there is a class, this is around 2015. They showed this for the case of a restricted Boltzmann machine, which is one of the older forms of neural networks. Last year, Physics Nobel Prize went to Hinton. Hinton was the father of restricted Boltzmann machine. Given what you have studied about Ising models now, you're totally in shape to go and understand what are restricted Boltzmann machines. It is nothing but an Ising model applied to doing deep learning. And it's no one uses it anymore, but it was the foundational form of how to do things. So people, Schwab and Mehta showed that effectively you are getting this, people call it a block spin structure. So what we did here was decimation, but you could do another operation where you're thinking about 4 spins at a time, right? 8 spins at a time. And in molecular dynamics and in my type of molecular simulations, people often call it coarse graining. So you have coarse grained out degrees of freedom of the system. In fact, and there is a whole lot of work that happens over here. And that paper got a lot of press around then because, oh, maybe the neural network is working so well because it is doing renormalization group, but it kind of disappeared. I mean, one of the classes that I taught from Boston, Pankaj Mehta was at the workshop I organized. He was there, so I went out for lunch with him. I was like, oh, I really love your paper. He was like, oh, it's useless. It never really got proven for anything else except restricted Boltzmann machine. But it is still a nice paper. It's got like 1,000 citations now or something. This is the last topic I wanted to cover. Any questions about this? Okay, that's very good. You are all now experts. So let me wrap up the semester in like 6 minutes before someone walks in through the door. So we did a lot of things, right? Let me open the syllabus. We started with a review of thermodynamics, right? And those of you who did not take 684, that's where you should be really careful. You might understand all of statistical mechanics, but there will be things involving thermodynamics that might trip you off. So it's important you spend some time making sure you know what are free energies, what are Maxwell relations, what is the condition for spontaneous change, and things like that. That was a whole semester that those who did 684 understood quite well. If you have done PCAM 481, then also you know what I'm talking about. So make sure to revise those things, because it's really thermo that is needed for StatMech to be useful. Sometimes people say thermo is like philosophy of science or science of science, but thermo is really what tells you profound relations. It just does not tell you how to calculate things, right? Thermo does not tell you how to calculate entropy. Statistical mechanics allows you to do that. So we started our statistical mechanics by talking about phase space, which is the most explicit description you can have of system, as detailed as possible. It's interesting that we finished with the renovation group theory, where the whole idea was to remove degrees of freedom, right? So it's a fitting end. Phase space is when you're thinking about all 3n class position coordinates, all 3n momentum coordinates. And ergodic hypothesis says that if you have an isolated system, every point in phase space is accessible and equally accessible. And in fact, Liouville's theorem, which we did not cover, but many of you saw, talks about the volume in phase space that the trajectory takes as it moves from one point to another. Right? We did not really cover that, but it's useful. So then we started thinking about ensembles. Our simplest ensemble was a microcanonical ensemble, or an ensemble where system is isolated from rest of the world. So it's isolated, the number of particles n, the volume v, and the total energy E is constant. So in this case, the probability of any given microstate is going to be constant. We don't know anything. We have no way of going and proving it, understanding what's going on, right? So it's like, if I had started teaching this semester and I did not know anything about you, I would assume all of you have the same level of StatMech knowledge, have the same level of preparation, right? As I interact with you, I get a sense, where is everyone, things like that, right? So without interacting, I cannot say anything. And that is connected to, and that's where the other thing from thermo becomes very important, natural variables. The natural variable for a system, if a system has natural variables NVE, the corresponding state function is S, or entropy. So S of NVE is connected to the number of macrostates you have in this system, which is the macro-canonical partition function omega. And KB ln omega gives us S. That was our first connection between thermo and StatMech. So you could take any problem and solve it using any ensemble. What you need to do is to get to the thermo. Once you solve for omega, you connect it to S. Once you have S as a function of NVE, you can unleash all your thermo on it and calculate everything, heat capacity, thermal expansion coefficient, whatever you want to do. But then that ensemble is kind of boring. It's isolated. What can you do? So we go to the next ensemble, which is canonical ensemble, where we allow energy to exchange. So the energy exchanges until we reach thermal equilibrium, temperature becomes constant. So now our natural variables are NVT. In that case, the state function is A, Helmholtz energy, and the partition function we calculated Q of NVT, which was summation e to the power minus beta E nu, right, over all microstates. So one way of thinking about it is that the microcanonical partition function is summation nu 1, right? Go to every microstate and count 1, right? Canonical partition function is go to every microstate and say, I'm not going to weight you equally. I'm going to give you a weight, which is e to the power minus beta E nu. Grand canonical partition function is summation nu e to the power minus beta E nu minus mu and nu, right? So it's just weighted sums of all states. In the end, you are counting possible microstates, right? And then we introduced some corrections for quantum mechanics here, right? We divided by n factorial to look about distinguishable particles and things like that. We divided by h cut to the power 3n to think about uncertainty principle. Often these things don't end up mattering because you're taking log of both sides and then you're differentiating things, so they just drop out. We don't really care about them that much, but sometimes they might. So, and we connected all of this to thermodynamics. We showed how thermodynamic averages correspond to log of partition function, how fluctuations correspond to how free energies correspond to log of partition function. But then there is a first class of averages, like average energy, which corresponds to derivative of the log of partition function with respect to something else. When you take a double derivative of the log of partition function, it corresponds to fluctuations in things. We looked at a lot of fluctuations. We showed a relation which comes across thermo all the time, and it even comes up in non-equilibrium thermodynamics, fluctuation relations. That was our first example of fluctuation relation, that fluctuations divided by mean go as 1 over square root of n. And this is a generic behavior for any fluctuation. It could be energy, it could be number, depending on the ensemble that you have. We applied these ensembles to a bunch of non-interacting ideal systems. We thought about occupation numbers. We thought about Fermi and Bose statistics, occupation numbers of those different systems. We looked at quantum ideal gases. We did a lot of heat capacity. We looked at phonons. We thought about density of states. We saw that how Einstein got it wrong, Debye got it perfectly correct. We looked at it, and the Debye relation was T cube as temperature goes to 0. Einstein was exponential of T. We looked at electrons, where the heat capacity was linear in temperature, and the whole idea there was only those electrons which are close to the Fermi surface are going to move, and the number of those electrons behaved in a certain different way, right? We have used the area of a right-angled triangle to do that. We looked at classical limits of quantum gases, and things turned out to be right. And then we went to interacting systems. We looked at classical fluids. We thought about distribution functions, but we ended up spending a lot of time about pair distribution function, radial distribution function, G of R, right? And we realized how rho G of R gives us the condition probability of finding a system. And then we went to Zwanzig's relation, which was super cool, and we saw people still use it in drug discovery, believe it or not. My student Shams is currently at a conference in Boston called the Free Energy Workshop, where basically half the talk are about using Zwanzig's relation. And people at DeepMind are trying to come up with neural networks which can basically get rid of Zwanzig's relation, but so far they have failed miserably. And then we showed how we could take Zwanzig's relation to go from a hot sphere to a van der Waals gas, and that was super cool. Then we did phase transitions. You, for the first time, hopefully, or maybe more than first time, you got introduced to the Ising model. We did not talk about lattice gas, nothing. And we talked about critical phenomena and exponents. We looked at mean field theory, the droplet argument. We looked at renormalization group today. We did not do the advanced topics, but I mentioned at different points about connections between StatMech and AI. One of the papers that was there in the 7 papers that none of you covered was a paper called Deep Unsupervised Learning Using Non-Equilibrium Statistical Mechanics. And I really want to end by showing you the citations of that paper, which is super interesting. Deep Unsupervised Learning Using Non-Equilibrium Statistical Mechanics. Okay, what I want to do is to go to this. Look at that. No one cited that paper. It's just picked up. Actually, this graph is false because the paper came out in 2012, right? So until 2021, no one cited this paper. And then this picked up. Did anyone actually open this paper and read it, apart from Disha, maybe? Because Disha knows about this paper. Anyone? If you open this paper, it will say, I'm going to sound a little bit like a fanboy, but you'll see what I mean. Jarzynski, 1997. This was a paper which was like, oh, in statistical physics, people have these ideas. Why don't we use it to come up with better models of neural networks, better neural network frameworks? And this paper really got picked up in 2020 because of something known as DALL-E, which many of you have probably used, right? Where you give it a command, draw me a photo of army in an impressionistic style, and it would come up with an image, right? DALL-E uses this paper. AlphaFold 3 uses this paper. And now this is the hottest thing in generative AI, which comes from non-equilibrium thermodynamics. So, StatMech continues to be a very important subject, which will continue inspiring a lot of things. And don't stress too much. Well, stress a little bit about DeFi-Move, not too much. Make sure to focus on concepts. You can score 100. It won't be a very hard exam. It will be conceptual exam. Okay? So, and I will try to grade these, everything, your midterm, your 2 homeworks, and they will be available in the IPST building around 3 p.m. tomorrow. So you can go and pick up everything. Good. Oh, yeah, and you must have received this teaching feedback. If you could fill that up, that would be great. It's anonymous. I don't have